Hello, this is the last lecture of the course, Audio Biometrics and Open Challenges in Biometrics. This is going to be a very short um, lecture. It's just a visual representation of some other biometrics that we can find um, in research papers, in some commercial applications. So just the intuitive idea of them. Just that you are aware that in addition to the main biometrics that we have seen, there are also some others that can find application. For example, when we have surveillance footage, which is common in security areas, in police applications, in smart cities, and so on, gait recognition can be very useful for providing additional biometric information. Perhaps that's not enough to really identify a person with high identification accuracy in a large scale database, but can be useful anyway. Gait recognition information as example, for example, as auxiliary information in some identification, forensic identification, for example. So methods for gait recognition, gait biometrics, are uh, follow basically two lines of work. First is describing the silhouette of the person as the person walks, and for that basically we're going to extract like the silhouette somehow, and then we're going to integrate the evolution of the silhouette across time in a kind of template. This template is usually an image template integrating the shape of the silhouette in an image representation. There are several methods for that. And on the other hand, the second group of methods um, uh, follow a kind of human tracking approach. So in that sense, it's a kind of similar to the techniques that you have seen with Alvaro for people detection and tracking. So some of them um, estimate or generate like a skeleton of the person using human body methods, and then track the different joints and the different elements of the skeleton across time, generating time functions, and then the problem becomes um, an analysis of the evolution of these time functions related to the skeleton parts. So this is a kind of more image-based approach and a time function-based approach. So in this time function-based approach, we can apply for gait recognition then matching methods similar to the ones that we saw in signature, DTW to match to different walk patterns, hierarchical models, and so on, because here we are going to have 10 functions. This is a visual representation of how we can integrate shapes across time for representing a gait pattern in an image. So imagine we have already segmented the person. So for this, the methods that you have seen with Alvaro are very useful. So we segment the person as a foreground, and then we discard the background, and then for all these segmented images in a walk in a gait video, the different frames, we just, as you can see, we average all these images. So on the average, and after we align them in the same location, rotation, so there will be a process of alignment, then average image, and here in that image we can extract features. Even we can do like data-driven recognition using CNN or deep learning approach. We have a large data set to train that network, or we can use some handcrafted features that have been demonstrated in research papers to be useful for characterizing the gait. For example, features related to the main area that is stable across time, or the area that is moving across time, and then some feature related to the contour of the movement and so on. So it's basically characterizing this kind of average walking pattern based on some features, or some data-driven learning approach. And the second approach, the one based on joints, so we just estimate the skeleton somehow, and then we track the different elements or joints, the different segments. We generate time function representation. This is time. This is, for example, angle of the hip, angle of the knee, angle of the. So there are many research works analyzing different elements in the body that can help for gait recognition. And then we will use this with a time function matching approach to compare gait sequences. Also, what we can do if we have some kind of sensing floor is to get the information of the footstep with a floor sensor. This is a representation of a pressure sensor in the floor. So as we walk, we can analyze the pressure pattern as we press with our feet the floor. And this is, for example, a sensor, a visual representation in colors of a footstep. As first we press with our feet in the floor, and then we can also apply like a dynamic representation of the different sensors or sensing elements in the floor, or just a static representation in a kind of image, low resolution image in this case. So each dot here is a specific sensing dot, so resolution is not very high, as you can see. And then with a time representation or a static representation, we can characterize the footstep, and this is also useful for biometric identification and other applications. For example, in this case, we can use that information also for fall detection in smart home applications or in other environments. And this can be complemented or fused, combined with gait biometrics, for example. Also, we can see many research papers working with images outside the visible spectrum, so with infrared images, thermal images, and images captured at the different ranges of the electromagnetic spectrum. So from X-ray, the highest frequency, so X-ray can be used, for example, for dental biometrics. So these dental radiographies can be used to characterize people based on that, and this has some applications, in particular for forensic applications, where after a disaster, a body can be corrupted, destroyed, and then the only evidence left stable after someone has been burnt, for example. The only evidence left is the teeth. So if we have a dental record of a person, that person can be identified based on dental biometrics. So this is visual biometric. This is the most important, of course. And then we have near infrared for faces, for hands, vein patterns. Iris also is usually captured in near infrared, as we discussed. Different parts of the infrared spectrum, near, short, and medium long infrared. And also there has been some developments on millimeter wave. And this is the lowest frequency that biometric applications have been developed, and this is the range where these kind of body scanners installed in airports operate. So with these millimeter wave scanners, radiation imaging can penetrate the clothing. So this is very useful to detect weapons and concealed weapons arms. And also with that imaging, we can estimate very in a robust way the shape of the person, the profile of the person, some texture of the body, and this way elements like clothing, like occlusions, um, are eliminated. So this is also a good way to characterize either as a combination with face, for example. We can combine face biometrics with this kind of shape as an additional biometric, and this kind of border control applications. So when you see this kind of body sensors, and there is also biometric information that can be extracted and used. In smartphones, which are growing and growing in importance for biometric identification, either for login or for securing certain applications, we can capture face, we can capture fingerprint, we can capture iris in some of them, we can capture voice, and also there is growing interest and development in acquiring the interaction signals like touchscreen signals as we swipe, pinch, and we move on a screen, as we type also with the virtual keyboard. So this kind of interaction signals, so you can see here an example, for example, two different users, two different sessions, the same application. So you see here some pattern. For example, user A, the kind of regions that the user A uses in this application, even across sessions. So this is the same application but in 2 different days, same application in 2 different days. So you can see, for example, that user B tends to use like more straight lines. There is some more curvature user A. So we can really extract some features from both of them, from these interaction signals, and those signals can help us to recognize or to characterize that user A, user B. This can be done for a specific application. This can be done application independent, like in general as the user is interacting with the phone in a long session or across sessions. And the same with typing patterns and any other information capture with the touchscreen or with the sensors inside. So accelerometer, gyroscope, any sensor is going to capture interaction signals that can be used to model the user, and there is a growing research line, and there are even some companies that are already using this information for improving the biometric recognition, like BehavioSec. BehavioSec is a company doing that. This is a system model of how we can use that information. So let's say, imagine we have like left to right swipe. We pre-process to detect if the swipe is left to right or up down, and then in order to generate different model into different conditions, we extract features based on the angle and various other features. We detect left to right, right to left, and then we have kind of a global statistic of how a general population behaves in terms of that pattern. We mix different patterns of different orientations, and then for each orientation, then we match using a GMM approach. So that's nothing very important. I'm not going to ask about a particular structure in the exam. It's just that you can see how we can build a system based on that information. Performance in terms of equaler rate for the system depends heavily on the amount of information. So it's not the same to really enroll a particular subject using just one session, several minutes, in comparison to model the user like if we have information for 1 day or for 1 week of interaction. So And typically for these kind of systems, the best approaches are these kind of statistical approaches like GMMs, hierarchical models, where we can integrate statistically growing information across time. So the more information we have, the better performance we will have for biometric recognition. Some references here of additional work, and nothing that you have to learn. This is also if we want to check for in the future this research line. And then let's see, to conclude the course, some ideas of what are interesting topics of future research. So if you plan some continuation of this master involving some kind of research proposal, and including for your own projects, and this research is somehow related to biometrics, I would say, or in general computer vision applications or pattern recognition applications. These are 4 challenges, 4 interesting research topics that you should consider. And these kind of challenges also show the limitations that nowadays we have in biometrics and in other related areas. So we have seen in the course that basically this is the standard architecture of a biometric system. So we have a biometric input. If the system is verification, we have also an identity claim. So biometric input identity claim. The identity claim selects one pre-enrolled template. I'm Julian, so I input my biometric. So enrolled template for Julian is selected here, and we are going to compare template against template. This is the enroll template, this is the input template. This can be, for example, a signature. I pre-process structural features like a global representation, global features. And this is the global features of the pre-enrolled template. We compare, for example, with Mahalanobis distance, and that comparison similarity score normalized. We do that. So we can design the different modules using handcrafted approaches, as demonstrated in the previous literature that work fine in terms of pre-processing, feature extraction, and so on. How do we build this system? So basically, what we do always is to look at an application, real application, data set, including many people, a large set of people, large set of data from all the devices, or at least a representative set of devices of the final application that we have in mind. Imagine we have signature biometrics, and we want to interoperate between all these devices, like specific signature tablets, signature acquisition devices, tablets, and so on. So we capture, let's say, 100 people, 1,000 people, many sessions. We compare all of them, genuine comparisons, imposter comparisons, in conditions similar to the ones that we are going to find in real applications. And then this is helpful to design or adapt the pre-processing stage, the feature extraction, the comparison, and so on. This way we design our system based on this data. This data, and also some knowledge that we have from previous research. For example, which are the best features, the most distinctive features, which are the best comparators, the best matchers, and so on. So basically, knowledge from previous works and experiments to set up and having a system really working well in this environment. So the challenge now, this is kind of a standard approach. This is what we have discussed in the course. Let's assume we have already designed the system here, and now we have like a new device or a new set of devices that are different to the previous one. They are similar, they share something, so they share the same nature of the biometric trait. So here we have also signature or a written symbol, but you can see that this is a mobile phone in comparison to fixed devices like the previous ones. So the statistics of the signals here in comparison to the signals before will be different. Ergonomics are different, so complexity usually here will be simpler. So the signals that we capture here are not well represented with the previous devices. So the idea is that if we want our system to operate in this new environment, and of course we don't want to really discard our previous system, we want to reuse the previous system to adapt it to the new scenario with less effort. So we don't want to start from scratch, capturing again a large data set here. We want to reuse the previous system to adapt it to work well in this new environment. So for that, we start from the previous system experiment knowledge, and just usually what we do is to conduct additional experiment to adapt to the new scenario. And this is something crucial and key and very important operationally for research, application, industrial application, especially now that we have very good systems to start as a base in signature in phase that we can directly download from the internet from many academic groups. So if we want to adapt, for example, let's say not only in signature, in face recognition, we can start from BGG face, which is an excellent face matcher, and then we can apply that, for example, let's say to do face selfies matching, and operating with faces covered with masks, for example, now for COVID. So we can start from BGG face and then adapt it to work in this new environment. And for that, there are several techniques. In general, there are many different methods, from domain adaptation, transfer learning, inductive learning, Bayesian adaptation, discriminative adaptation. These kind of general adaptation techniques are very important for doing this domain adaptation. We're not going to enter that, but in fact this is a very important research area that it's now very popular in general machine learning, and in particular for practical applications of this kind, where we have a very good system and we want to adapt it to new application, is a challenge in many occasions. Second thing is incorporating contextual information. Assume we have the system. The system was designed using a knowledge base. Now we have a system in operation. So it's very important in many practical applications of biometric to have like a module that it's continuously estimating the input quality, environmental quality or environmental conditions, let's say illumination, temperature. So we are kind of analyzing the environment and the input signal quality, like for example in fingerprint, the NFIQ, the NIST Fingerprint Identification Index. And then with that, we adapt some parts of our system. Perhaps based on that, we modify the pre-processing, we modify the score normalization, we modify the decision threshold. So a smart, adaptive way to really include contextual information continuously over time. There are some methods to do that, but the final performance of a biometric system will depend heavily on that. If we just fix everything and put the system to work, if we have some deviation of the sensor, of the environment, then the performance will be degraded significantly. So we have to adapt with that. Third challenge, we have seen in some biometrics, especially in the behavioral biometrics like signature, behavioral biometrics from the interaction with the smartphone, speech, gait, and so on, that different subjects can behave very differently. For example, in signatures, we can have some subjects of very short signatures, others with very long signatures, very complex signatures. So ideally, instead of having all the templates and all the processing steps designed in the same way for all subjects. Many times, especially in behavioral biometrics, there is a large improvement if we design or adapt different steps of the architecture for different subjects or for different groups of subjects. For example, let's say in signature, for signers, for people with simple signatures, we can have like simple template. So imagine only 10 features in a global feature set. And for complex signatures, we may have a different kind of template. Let's say also a global feature, but instead with 100 features, more features for more complex signatures. Or we extract more sophisticated features, or we compare with a different method. So we can do this kind of user-dependent or group-dependent pre-processing feature extraction. So we can adapt different modules to different people or different groups of people. And for some biometrics, like speech, signature, behavioral biometrics, but also for face, this can be very beneficial to adapt parts of the system to specific users or group of users. This can be also, for example, useful in aging. Aging is a very challenging aspect, especially if we want to compare enroll template to input template with a difference of years. If we know that in different ages we have different behavior, then we can adapt when we have people with different age or different conditions of comparison across time. And then the last one is exploiting big data. We have seen that we have this kind of database of enrolled templates, and the size of the database is very important for designing, for building our system. In some cases, like face recognition, we have now datasets, public datasets, in the order of millions of images. This is not public in all biometrics, so finding a good dataset for research and for development of millions of fingerprints, for example, or signatures, is much more difficult. Only agencies like forensic agencies, national authorities have this kind of large-scale datasets. But if we have this kind of large-scale dataset, we can then have like the raw data, let's say signatures, raw data, or we can have some kind of anonymized projection. So from a signature we can project, for example, with a subspace projection or other kind of even cryptographic projection, kind of hashing. So each signature will be here like a vector that represents the signature, but in an anonymized way. So we can have this representation from multiple signatures, let's say thousands, millions of people, and that we manage that data using a big data infrastructure. And from that large data set, we can really extract very useful information, very stable, discriminative and representations using deep learning. This has been done in face. We have excellent face models, face embeddings. This is a topic of research now in signature and other biometrics. Fingerprint, for example, still hasn't really exploited all the capabilities of the deep learning. Still, the best methods in fingerprint are handcrafted. So deep learning is being now investigated in almost all biometrics, especially when we have this kind of large-scale data, millions of samples, and we want to really exploit, take the most out of that big data. That's all. It's been my pleasure to be with you remotely. I hope that you stay safe this next few weeks, and I will be available anytime from now to the final exam and to the receipt exam through Teams, through email. So if you have doubts, if you're not sure how to really study the subject towards the final exam, just let me know, write me. So see you.